So where we really need Lewis structure is when it comes to covalent bonding. So here the electrons are shared. Here we're talking about nonmetals reacting with other nonmetals, forming molecular compounds. When we named molecular compounds, we looked at the formulas and we used numerical prefixes to indicate how many of each there were. We can't use ion charges to predict the formulas, but we're going to see that Lewis structure can help us to predict what formulas might be stable and what are not. So in a covalent bond, the electrons are shared. We represent the covalent bonding as neighboring atoms sharing their valence electrons to obtain an octet. If you share something with someone, then it belongs to both of you, right? So it like does double duty. It belongs to me and it belongs to you. So let's look at hydrogen and oxygen Lewis structures. So here's hydrogen. How many valence electrons does hydrogen have? 1. And oxygen, how many valence electrons? 6. So I'm going to stick them in like this because it's going to be convenient for what I'm planning to do. So oxygen wants to gain 2 electrons. But hydrogen doesn't really want to give up that electron. And so what's going to happen is they're going to share. So these guys are going to share an electron instead of transferring an electron. Those shared electrons count for both. So hydrogen looks at these shared electrons and says, I've got 2 electrons. I'm just a little person, and so that's all I'm trying to get. I want to be like helium with 2 electrons. I'm good, I'm happy now. Oxygen looks at these shared electrons and counts them as her own, 2, 4, 6, 7. Oxygen's not quite happy yet. So oxygen's going to look for someone else to share with. So let's put another hydrogen over here, another hydrogen with 1 valence electron. This hydrogen is willing to share that electron, and so it will share with the oxygen. So the oxygen sees all of these electrons as belonging to her. 2, 4, 6, 8. I'm going to do a lot of counting to 8 by 2s. 2, 4, 6, 8. Okay, so this oxygen has an octet. She's happy. What about the hydrogens? Well, they've got 2 electrons. The hydrogen counts its shared electrons, and so the hydrogen feels like it has 2 electrons. And that's all that hydrogen needs. Hydrogen follows the duet rule. It just needs 2 electrons to be happy. Easily satisfied. Any questions? Yeah. Hydrogen, helium, and sort of lithium as well. There are other things that violate the octet rule, but we're not going to talk about a lot of them. So the one you really need to remember is hydrogen, because helium doesn't form compounds, and so we're not going to be writing Lewis structures for helium. Hydrogen is going to show up in a lot of things, and you have to remember that hydrogen is satisfied with 2. So that's the thing you need to remember. So I'm going to draw that again. So here we have hydrogen, oxygen, hydrogen. And we're sharing those electrons. So we have bonding pairs and we have lone pairs or non-bonding pairs. This is a pair of electrons. A pair is 2, in case you were wondering. Pair of electrons. So this pair is being shared between the 2 atoms. That is creating a bond. When you share something with someone, it kind of brings you together, right? You can't effectively share without, having some sort of a relationship. So there's a bonding pair, and this is a bonding pair. This pair of electrons on oxygen is not involved in bonding. It's just sitting there on the oxygen. It's called a non-bonding or lone pair. So this is a lone pair and that's a lone pair. Let's label those. So we've got lone pairs. That one and this one. And then we've got bonding pairs. Bonding pairs, this one and that one. We need to be able to identify which ones are lone pairs and which ones are bonding pairs. So I have shown this bonding pair as the electron from oxygen and the electron from hydrogen, and I drew the line and connected the dots. I like that because it helps us to see that that's 2 electrons. It gets a little tedious though, and so oftentimes we represent a bonding pair as just a line. So you will often see the Lewis structure for water drawn like this. And that has some advantages as well. So this line represents 2 electrons connected, shared. So it's just, we connected the dots. So when we look at this, we see oxygen has 2, 4, 6, 8, and each hydrogen has 2. And so oxygen has an octet, the hydrogens have duets, everybody's happy. One of the nice things about Lewis structures is that you can make everybody happy. It doesn't happen in real life, does it? Questions? So we've talked about diatomic molecules, right? The 7. And, why do they do that? Lewis theory explains this. Let's look at bromine. I'm going to make bromine purple because I'm tired of blue. How many valence electrons does bromine have? 7. So 1, 2, 3, 4, 5, 6, 7. Is bromine happy? No. Let's draw another bromine. So here's another bromine. This bromine also has 7 valence electrons. This bromine says, hey, give me your electrons so I can be happy. And this bromine says, no way, I want one of your electrons so I can be happy. Neither of them is willing to give up their electron because they don't want to become a positive ion. So they decide to share. So we share those electrons. Now each bromine has an octet. This is why bromine atoms don't go out by themselves. Because when they go out in pairs, I think of this kind of as like holding hands, they're more comfortable, they're more stable. So bromine forms a Br2 molecule. Because when it does that, it has an octet of electrons for each atom. Hydrogen is also a diatomic element. So 2 hydrogen atoms, they each have 1 valence electron. Not happy. If they share their valence electrons, now they each have 2. They have a duet, and so they're more comfortable, they're more stable. So hydrogen is a diatomic element. Any questions? Nature is all about things going to the lowest energy state. Energy is what drives much of the things that happen. Well, atoms can share more than 1 pair of electrons. So let's look at oxygen. Oxygen is also one of the diatomic elements, isn't it? So oxygen, we've learned, has 6 valence electrons. So I'll draw that with 6 dots. And then let's draw another one over here with 6 dots. Someone in Roseville, California is calling me. I don't know anybody there. So these oxygens, nobody's willing to give up electrons, so they're going to share. So they'll share their electrons there. Are they happy? No. They're happier. Now they've got 7 valence electrons instead of 6, but not quite. So they could also share another pair of electrons. So that's a little difficult to look at. So let's draw it a little differently. They're sharing 2 pairs of electrons. We often draw this with just a double line here, and then we put the lone pairs on. So now we see this oxygen counts 2, 4, and it counts all of the shared electrons, 6, 8. And this oxygen counts 2, 4, 6, 8. They both have 8 valence electrons by sharing. So oxygen atoms also go out as diatomic molecules to share. This does not apply to oxygen in a compound, because then oxygen is going to share or transfer electrons with other atoms in order to be happy. So when we see this double line, we've envisioned this connecting the dots between 2 pairs of electrons. This is called a double bond. Any questions? So a double bond is 2 pairs being shared. Double bonds are shorter and stronger than single bonds, because the more you share with a person, the closer you get, right? And the stronger your bond. The distance between the oxygen nuclei is smaller. It's 121 picometers. In a single bond, it's 148. So the double bond pulls the pulls the atoms closer together, and it's stronger as well. Let's look at nitrogen. So we've looked at hydrogen, and we've looked at a halogen. All the halogens have 7 valence electrons, and so they're all going to act like bromine did. And we've looked at oxygen. The one diatomic element we haven't looked at yet is nitrogen. So, Lewis structure for nitrogen. So here's nitrogen, and it has 5 valence electrons. And another nitrogen atom has 5 valence electrons. I'm drawing the dots in a particular order because I know what I want to do with them. Well, how can 2 nitrogen atoms share electrons and both get octets? Well, let's start by sharing that one. This nitrogen now has 2, 4, 5, 6. Not enough. Let's share some more. 2, 4, 6, 7. Almost. Let's share here as well. 2, 4, 6, 8. So this will often be represented like this. Where we understand that these lines represent a pair of electrons. So let me draw that out. We still have the same number of dots, but when we share these, they count for both. So for this nitrogen, counts 2, 4, 6, and 8. Cool, happy. 8 electrons. This nitrogen counts 2, 4, 6, 8. The octet rule. They're transferring or sharing electrons to get 8. So that's a triple bond. So my husband is also a chemist. His office is just over there, right next to mine. His students call him Dr. K. I'm Mrs. K. So this is me, and that's my husband, and we have a triple bond. This is James and Zach and Tommy and Michael and Emily and Andrew. A triple bond, 6 children. So triple bond, 3 pairs of electrons shared between 2 atoms. The double bond was shorter and stronger than a single bond. A triple bond is even shorter and stronger. So, for example, here in nitrogen, a triple bond is a length of 110, and in a double bond, it's 124. So sharing that extra electron pair pulls them even closer together. Nitrogen is not a very reactive element. Oxygen's reactive. It'll combust. It is the essential ingredient for combustion. We know that hydrogen is reactive. The Hindenburg exploded, right? Nitrogen is not very reactive. Nitrogen is one of the main components of air, and it just doesn't react much at all. The reason for this is that we've got this very strong, short, triple bond holding those 2 nitrogen atoms together. And so it takes a lot for nitrogen to react with something else, because you have to break those bonds. Any questions? Mm-hmm.
So why is it that only those form like that is a non?
Well, sulfur and phosphorus are right in there as well, but they don't form diatomic molecules. They are also solids at room temperature. Phosphorus and sulfur, we didn't really tell you this, but they do form molecules. I know sulfur forms an S8 molecule, and there's at least 2 forms of phosphorus. I don't remember off the top of my head what they are, but they don't form diatomic molecules. And I think that might be because they are larger, and so for them to form double or triple bonds with each other would be uncomfortable. It'd be awkward.
Well, aren't bromine and iodine even larger than them?
That's true, but they're forming single bonds. Yeah. So there are reasons that the others don't. They're not easy for me to explain at a 3A level. Carbon forms bonds with other carbon atoms, but not in individual molecules. Diamonds and graphite and Buckminster fullerene are different forms of carbon as an element where it's chemically bonded to other carbon atoms. Did I answer your question? It's a good question.